Okay, so once again, good morning, everyone. So our topic for today is about software architecture. No, so most commonly, no, especially during our time, no, in the undergraduate program, specifically in software engineering, no, we always consider the software architecture in design. When we say software architecture, of course, of a system, it represents the design decisions related to overall system structure and behavior. No? So architecture helps stakeholders understand and analyze how the system will achieve essential qualities such as modifiability, availability, and number one issue at present is the security. So software architecture support analysis of system qualities when terms are or when a team are making decisions about the system rather than after implementation, integration, or deployment. Since you are enrolled in the undergraduate program, no, specifically right now, the higher year is now presenting their title proposal. No, we always see to it that the student or the student who are enrolled in capstone project be able to address the of course the implementation, integration, and deployment. So whether designing a new system, evolving a successful system, or modernizing a legacy system, this timely analysis enables teams to determine whether the approaches they've chosen will yield an acceptable solution. Because we need to consider a lot of things, no? Again,
Okay, so as I mentioned earlier, no, an effective architecture serves as the conceptual glue that holds every phase of the project together for all of its stakeholders, enabling agility, time and cost savings, and early identification of design risk. Now, actually yesterday, no, we wanted, no, of course, to secure that the proposal of the student must be at least with initial talk or an approval from the clients. No, this is very important, no, because building an effective architecture that enables rapid product delivery for today's needs while also addressing long-term goals can provide challenging, no, because failing to identify, prioritize, and manage trade-offs among architecturally significant qualities often leads to project delays, costly rework, or worse. Now, that's why last day, since I am one of the panels, no, actually, I always inform them that the prior approval is specifically, no, if your proposal is for the government agency, we need to accept the fact that the government have 1 year ahead budget allocation, right? So let's say, for example, you have a proposal for this local government, no, and there is no any budget allotted for this type of projects. So you mean to say you will be able to graduate 2 years after? So it is very important for us to know if there are certain budget allotted for this type of project. So again, an effective software architecture supported by agile architecture. Practices enable effective continuous system evolution. So siguro naman this time, no, nobody will be able to use the SDLC. We're looking forward for the application of for the use of different tools like agile, no? Because such practices include documenting the architectural elements and interrelationship intended to achieve the key qualities, no, repeatedly evaluating the architecture for fitness with respect to an organization business and mission goals, and analyzing the deployed system for conformance to the architecture. So when performed correctly, these practices enable predictable product quality, fewer downstream problems, time and cost savings, and integration and test, and cost-effective system evolutions. So I just want to show you a video presentation on how this will be actually an introduction of a what we call this one, a software architecture, no? Because again, it is very important to lay down as early as possible, even during your title defense, no, the software architecture that you're looking at. Because as a graduate students, no, we always looking that it must be one step ahead than the undergraduate program. And in the CHED requirements, it is always advised that it must have at least an IT technology application. So most commonly right now, no, in PLMO, no, we are always suggesting the use of, let's say, mobile technology, IoT, and so on. So at this point in time, you are now ready, no, to think what are your possible capstone project during your last year or final year in your MIT program. And again, me particularly, I'm always asking related to software architectures, no, how you'll be able to lay down, because no, during our first year in undergraduate program, our professors help us, no, to understand on how we'll be able to use the pseudocode, flow chart, no. And during our time, we have a data flow diagram, we have ERD, we have architectural design, and so on and so forth, which is also a good starting point for you as an MIT students. No, we need always to learn and relearn, no, the previous lessons that are imparted by our professor, because it's too important during your capstone year, no. So again, I just want to share my screen related to the video presentations of a structural architectural software architecture, I think.
Buildings or other structures. A good design can make a structure survive and be admired for years, or fail even to stand. It's the job of the architect to join both art and science to make sure all the pieces of a building come together in a good solution. Similar to architects, as a software engineer, you will also need to mix art and science to deliver solutions in a satisfactory way. But instead of bricks, you will solve them with code. Hi there, I'm Christian and you're watching The Dev Story. Today I will be starting a new series of videos covering software architecture in a practical way. In this series of videos I will be covering many concepts and fundamentals of software architecture. So hopefully by the end of it you will be more prepared to tackle software design challenges and have better discussions and even be more prepared for a technical interview. So without further ado, let's start. Software architecture has many definitions. One of the most famous one is from Ralph Johnson, where he says, architecture is about the important stuff, whatever that is. But what is important stuff? In the software architecture, we focus more on the structure more than the implementation details. Software architecture is also about making the expensive choices that are costly to change after they are implemented. It's also about making explicit the core decisions that will allow the software to have high quality. Concepts are better understood in practice. Let's build an e-commerce site and see how that looks. So for example, in our e-commerce site, we need to allow our users to do certain things, like search the inventory, check reviews, buy a product, review past orders, and maybe other features as well. These are the functional requirements of the application. Besides of what the system should do, we also need to focus on how should the system behave. These are also called the non-functional requirements. These are sometimes defined as the utilities that the system can have, like functionality, reliability, usability, efficiency, these kind of things. For example, in our e-commerce site, let's say that we want it to be maintainable for several years, and this is a maintainability requirement. We also want to be able to serve millions of users. In this case, it's scalability. We also want to make it available 24/7, which is reliability, to make sure that the system is very stable. We also want to have good response latency, which is efficiency. And we can have many others. Finally, besides functional and non-functional requirements, you might also have additional restrictions that will limit the options that you will have for your architecture. So for example, we could have some legal compliance, cost, time to market, standards, etc. Several restrictions that will limit the number of options that we will have to design our system. Let's say in our e-commerce side, we need to comply with the European privacy law, GDPR. So with that, we need to take into consideration in our architecture how to handle that. So after you get the context, you know all the things that the system needs to do, how it should behave, and what restrictions are in place that you need to take into consideration. So after you have all of these things, you need to prioritize them. Some requirements and restrictions will conflict between them. For example, if you have a strict time to market, maybe you need to drop some features. There can also be other things like non-functional requirements that need to be prioritized. So for example, in our case of the e-commerce site, we might not care too much about portability because we will have a strong control of where is going to be deployed the application. And after it's deployed in there, we don't plan to move it to other platforms. So we could drop portability in favor of scalability or maintainability. So after you have prioritized the list and you have made this trade-off, you need to think about if it's acceptable or not. So after it's acceptable, then you start designing the architecture. How do you start designing the system? So the first thing is, once you have it prioritized, start with one important thing at a time. If you try to tackle everything at the beginning and try to think about all the possible scenarios in the future, you might end up having an over-engineered solution. And this is not good because it is an unnecessarily complex system. There is also an acronym for that is JAGNY, that you ain't gonna need it. So if you're not sure about something or if it's not prioritized, then try not to tackle at first. Try to postpone it to when you have better context and can make a better decision about it. Now that you have this, you might start thinking about what are the possible architectures that might fit your system. For that, a good book that I recommend and that is useful for me and is this free ebook from O'Reilly that is Software Architecture Patterns. It is a good book to get a grasp of different architecture approaches. And you can see several architecture patterns like layered, event-driven, microkernel, microservices, and space-based. This book shows pros and cons of each of these patterns and might help you at the beginning when you're designing the system, what to look for and what would be best for your system based on your current requirements. So we have decided what are some of the features that we want to have our system implemented. We have also mentioned that maintainability is one of the non-functional requirements that is very important for us. So with that, we can start designing our system and we can take, for example, a layered approach. We can have a database or a storage layer where we would store data. Then we will have a logic layer where we'll have the backend servers that will be taking care of handling any business logic that we want to handle. And then the visualization part, or UI, where we'll be allowing the users to interact with the system. And this is how we get to the layer architecture. So here we have defined the architecture with the structure that the system will have. The features can then be implemented following this layer architecture. And if you want to learn a little bit more about how to implement the features in a scalable, nice way, then I recommend you to check out my other video about design patterns. It's very typical in web applications to use a layer architecture, but it's not the only architectural pattern that we can use. There is no silver bullet, so make sure that in your context you look to different approaches and pick the architectural pattern that will better fit your use case. It's also normal that the architecture will evolve over time, and sometimes even in unintended ways that will make expensive changes to the architecture. So you need to make a balance about foreseeing the certain things that you will need to cover versus the things that you need to prioritize in the short term. If you try to tackle everything, then you can end up having an over-engineered solution. One of the most expensive things can be scaling. So in our case, we already have the architecture. How can we make it scale to serve millions and millions of user requests? For that, check out my next video. And that's it for today. Thank you very much for watching.
Actually, his video is very practical, no, easy to understand, no? And actually during my time when I was a student, no, in my doctorate degree, I always see that I could able to watch a YouTuber who are very good actually discussion, no? Because there are certain foreign, no, speaker, especially, no, from India. It's too hard for us to understand. Even they talk through English language. So this will be a continuation, actually.
And you're watching a dev story. This is the second video of the software architecture series where I'm covering core concepts in a practical way. If you haven't, check out my other video first. Just recapping from the previous video, we are building an e-commerce site and we have a basic layer architecture in place. So at the time we started with the layer architecture because we're covering the maintainability aspect of the software. With that architecture, we are also able to deliver the functional requirements that we need. Now it comes to mind the question, will it scale? And we need to define what is exactly what we need to scale. Do we need to scale the number of concurrent requests that we can handle? Or do we need to scale the amount of data that we are handling? So let's assume both. In the previous architecture, let's assume that we have all of this in one server. So if we want to handle 100 users concurrently, that's fine. We can support it. 1,000 users, probably fine. 50k users, let's check. But probably we need to add more hardware. In this case, this is called scale up or vertical scaling. Vertical scaling basically means to make the nodes stronger, right? Like if you have one server, make the server stronger, faster, adding more hardware, basically. Make optimizations on the software that would allow it to process more requests with the same number of resources in one server. Now let's say we want to handle 10 million users at the same time. In this case, probably only having one server won't be enough. So in this case, we need to do horizontal scaling or scaling out. Horizontal scaling basically means splitting the load between different servers. It gives you scalability but also reliability, because you will have more redundancy. And it's usually the preferred way to scale. When splitting into multiple servers, you need to take into consideration if you have a state or not. If you don't have a state, no problem. You can just put different servers and have a load balancer that will direct the traffic to different servers, and that's it. But if you have a state, then you will face the CAP theorem. I won't talk about the CAP theorem in this video because it's a big topic on itself. So we can simplify the services, for example, making them stateless. But the database or any storage service will need to face the consequences of the CAP theorem. As I mentioned before, when we're thinking about horizontal scaling with the state involved, we need to face the CAP theorem. And this has certain implications for the database. For example, we need to consider the consistency level that we need to have. Do we need to have a strict consistency? That means that whenever you save, that data is immediately available for everyone? Or can we handle eventual consistency? Basically, that means that when you write, it will take some time for all the clients reading the data to get that right. We also need to think about if we need to read more or write more. So depending on that, we will also take one approach or the other. Horizontal scaling isn't something cheap to do. So that's why it's very important to get it as soon as possible when you know that your system will grow beyond certain scale. There are different ways that you can achieve horizontal scaling. For example, you can have a load balancer that will direct the traffic to different servers to optimize the load or performance of the system. In this case, with the load balancer, we assume that all the servers have access to the same data. Then we can also split the data. So in that sense, we can have sharding or partitioning where we split the data between different servers. By splitting the data in multiple servers, you are able to scale each of them independently. Many systems work like this. For example, Flink or Kafka work like this. You can split the data following different approaches. For example, you can do a vertical split by feature, or you can have by value. Let's say we want to split the data between America's user base, Europe, and Asia. Or we can also do it by hash. So for example, by hash, you can imagine a hash table where we get the value that we want to select in which database is going to be stored. In this case, let's say we have a user ID, so we hash it, and we can say that depending on the hash, we will store it in one bucket or the other. In this case, the buckets are the database's servers where it would be. Then you can also scale this by using consistent hashing, but that's a topic for another video. Another thing that we can do with the data is to have replication, where we can have multiple copies of the data in different servers. Replication is very useful when you have read-intensive applications, right? So if you can replicate the data between different nodes, and if you know that you're going to read more, then you can just use those nodes to read, and you can have eventual consistency to update those nodes. Following with this approach, we end up with this architecture. We still have a layer architecture where we have horizontally scaled our system, so we have multiple nodes handling the load and also multiple nodes handling the data. Now millions of users can use our site because we have been able to split the load and the data between different servers. But this came up with some trade-offs. It was expensive and the cap theorem had to be considered. Now that we have multiple servers, instead of having only one, there is more latency between the calls between different servers. So that would be making the system a little bit slower. It's what I mentioned in the first video about sometimes there will be conflicts between some non-functional requirements and others. Users are expecting to have fast responses. We can also save a lot of resources and make tons of money if we're able to serve them faster. Can we be faster? How can we do it? Check out my next video to know more about that. That's it for today. Thank you very much for watching. If you like the video, don't forget to click like and subscribe.
Okay, so as you can see, no, he will be able to discuss about the scalability. Again, we just not only use the ISO 9001, no, because majority of our students, no, especially us, no, during our time, since we don't have a totally understanding about ISO 9100, no, most commonly we are adapting the perps, no, the functionality, usability, reliability, no, and sometimes they were also using the user friendliness, no, but most commonly we are adapting the perps and ISO 9001. But we need to understand it well one by one, no, as you can see here, no, based on the discussions of the video presented by one of a good speaker, no, when it comes to software architecture, no. Actually I used to attend his training in other country before, no. That's why it is very important, no, a while ago he discussed, no, about the scalability, which is too important also. So this time we just wanted now to move on the cache, no, the cache. A while ago he discussed about the distributed system software architecture. So this time, how about the distributed cache, no? So later on, I will share to you the link of his YouTube account, no, for you to understand not only the software architecture, but there are certain topics, no, that he will be able to discuss clearly and practically, in a practical way, actually, no. So I'm not endorsing him, but I just wanted to you also to know on how you'll be able to understand some specific, no, specifically for the graduate program. Actually, even the undergraduate student was able to understand his explanation.
And you're watching a Dev Story. In this video, I will continue with the software architecture series, and if you haven't watched the previous videos, I recommend you to watch them first. So just recapping, we have horizontally scaled a layer architecture, taking into consideration some limitations like the cap theorem. With so many servers, we now have larger latency, even though we can now handle millions of requests per second and millions of users. How can we make the system faster? One way to do it is by using cache. A cache is a component that stores data so future requests that request the same data can be served faster. We can have different flavors. We can have a CDN, that is a content delivery network, that serves as a cache for the users to not having to download every time the same images or the static assets. We can also have in-memory or local cache that you can have on your service to allow to respond faster to the request. And you can also have other things like distributed cache, like Redis or Memcache, where you can use it as a layer before hitting the database, for example. Basically, any layer in the architecture can have cache. Of course, nothing is for free. Adding cache also complicates our system. And cache can be one of those things that improves a lot your system, but also can cause a lot of headaches. For example, Phil Carton says, there are only two hard things in computer science: caching validation and naming things. We already know how hard it is to name things in computer science. Caching validation is even more complex. Some of the complications that we can have with cache is, for example, the update latency. Let's say, for example, that we're looking for a product. Let's say we're looking to buy a new computer, and the search results can be cached. So every time you look for a computer, you don't need to hit the database. So you get a cached result. But if we add a new product and the cache is not invalidated, then you might get results that are outdated, like maybe that product is not available, or maybe you are missing a product that is available. So you need to configure how quick or not will be the invalidation of the cache storing those results. If it's too fast, then it's basically as if you didn't have any cache. But if it's too slow, then you might be showing results that are out of date. You also have cache misses. So if you, for example, you have a load balancer where you are directing the traffic to different servers, if you have in one server cached certain results, let's say the user card, if the user is then sent to another server, this second server won't have the cache card there. If it doesn't, then it will have to calculate again what is the current state of the card in order to store it in the cache. And it can happen several times. So if you keep switching between servers, then you will always be hitting a cache that is empty. It's basically also as not having a cache. Just designing the cache will be very hard. And if you have multiple levels of cache in different layers, it can become even harder. Thanks to cache and scalability, now millions of users can access our e-commerce site and get fast responses. Cache is something that can be added at a later stage. It's not so important to get it at the beginning because it's more of an optimization technique. Nevertheless, it has to be taken into consideration in the architecture, but as we mentioned before, it's something that you can tackle one thing at a time and evolve the architecture accordingly. So first we made it maintainable, then scalable, then performance. What other things can we do to improve performance, maintainability, and scalability of the system? Keep watching my series to keep knowing more about them. And that's it for today. Thank you very much for watching, and if you like the video, don't forget.
Okay, so again, the advancing of the practice of the software architecture is very also important. The SEI, no, the software engineering, no, has been and continues to be at the forefront of establishing, maturing, and disseminating proven techniques to help you achieve the benefits that a good architecture can deliver. So we have a lot of developed range proven methods such as architecture trade-off analysis method that can help organization at any stage in the software development lifecycle. And regardless of whether they follow an in-house, acquisition-based, agile, or waterfall model, whether the context is cloud migration, architecting of artificial intelligence and machine language, modernizing legacy system, DevSecOps, no, operations, or continuous evolutions, we need to hone our expertise by applying research to real customer projects across many domains. No? So the possible techniques and practices could help the organization, of course, is number one is reduce business mission risk, such as risk to cost, schedule, time to market, and others. Enable agile iterative development, reduce development risk, develop quality products and services, modernize legacy system asset, the architectural origin and consequences of technical debt, and analyze the alternative. Okay, so I think that's it for this topic. There are certain things that because software architect is one subject actually, no, there's also one courses, no, that we need to continue reading. The video a while ago give you a possible books, no, that we could consider, no, especially if you wanted to not perfectly done your software, no, but for you to be more guided, no, in developing your own software. That is actually a dev story, no, ang kanyang pinaka nung sa YouTube, no, a dev story. So So a while ago, no, we already discussed the different, no, but we have, I don't know if you are still familiar with the event sourcing, Saga pattern for microservices. We have the event-driven architecture is also another an interesting, no, an interesting discussion. I just want to share also this one, no. This will be the last, no. This will be the last, no, the event driven architecture, which is also a good, no, a good inputs, no, related to software architecture. Okay.
You may see this one as the fourth video in the series of the software architecture introduction. And actually I will be building up on the example from there. But actually you can start directly from here. So with the additional introduction, let's start. First, let's get into the concepts. On one hand, we have an event. An event is basically something that happens. On the other hand, we have a command. A command is an order, a request that you have to another party to give you a response. An event can be communicated in the form of an event notification. And a command can be communicated also in the form of a message. These two things are very similar in terms of the information that they contain. And you can see that an event notification will also be referred sometimes as a message. In practice, you will see many people referring to both of these things as events. And if you are a purist, you might disagree with this and you might be right, because an event, as we mentioned, is something that happens. It's not a notification or the message associated with events. And it's also very different from the intention of the command. And we will see that the intention is very, very important later. But since in this channel we try to focus more on the practical side, we will call this an event for the rest of the series. So this event or message have different characteristics, as we mentioned before. It could contain data associated with the event or the command, or it could just be a notification that something happened. Additionally, something that is very important is that it is immutable. This event is the base of what is called event-driven architecture. There are many definitions of what event-driven is, if it should be only event-based, or if it also includes other types of messages. So sometimes you might see also event-driven architecture mentioned as message-driven architecture, or message-driven architecture being a generalization of the event-driven architecture. If you want to get more in depth into this topic, I recommend you to watch Martin Fowler's presentation, The Many Meanings of Event-Driven Architecture. But this is what I mean with event-driven architecture throughout the series. So bear with me and let's talk a little bit more about the details of it. Event-driven architectures usually have at least three components. One is the producer, another one is the broker, and the last one is consumer. Basically, a producer creates the events that are going to be redirected by a broker into the right consumers. The consumers will react to this event and execute the things that they need to execute. These components go by different names. And event-driven architecture or message-driven architecture are usually referred to as publish-subscribe model too. So why we will use event-driven architecture? So one of the benefits that it provides is that it allows you to decouple different components. It also allows you to invert dependencies. And finally, it also allows you to scale better. And I will show you that right now in an example. So usually you will have one service that wants to communicate to another service. For example, service 1 to service 2. When you do this, there is a coupling between the service 1 and service 2. Like service 1 needs to know about the existence of service 2 in order to call it. And this creates a dependency. In an event-driven architecture fashion, we will still have the service 1 and service 2. But instead of communicating directly from service 1, what we will do is to send an event. Now service 2 needs to know about this event and process it. So in this way we have inverted the dependencies. We have also decoupled them, because service 1 doesn't need to know that there's a service 2, neither does service 2 need to know about service 1. They just need to know about an event of producing and consuming this event. Additionally, as we mentioned before, events are immutable. And by being immutable, it means that they can be processed in parallel with other systems too. So this event can be consumed from additional services if we want to execute additional things. Also, when you have communication using events, events can be persisted. And this way the information can be retrieved even at later stages, and not only during the call, like it happens when you just make a direct call between one service and the next. there is also no single point of failure, so the system is more robust. Basically, when you're communicating from service 1 to service 2 in the regular request response approach, you need both services to be online and active to receive the request. But in the event-driven system, one of the two systems can be down after you have sent the event. The event will be persisted in the broker until a consumer reads it. This allows you to have more flexibility or more robustness, let's say, in the case of failures. Some cons that the event-driven architecture have are, for example, performance. Before, you just call from service 1 to service 2 directly. Now you have an intermediary that will be redirecting the messages to the right services. So this adds some performance hit to the architecture in pro of scalability, as we mentioned before. There is also consistency. When you are calling directly from one service to another one, everything is happening kind of at the same time. But when you have an event, there's always a delay between you send it and another one reads it. And if you have multiple services reading from the same event, each of them can read it at different times and they can be out of sync. There can also be more complexity when you're building event-driven architectures because it's harder to track what happens and when it happens and how the communication lines are happening throughout the system. When you have direct dependencies, you know exactly who you're calling and when you're calling them. So the important thing is, when then should you use an event-driven architecture for your solution? And there are different cases. The main one is when scalability is more important than performance. There's also when you want to have that data replication. So when you have data replication, it's basically you need the same information in multiple systems. So instead of calling different systems to pass out information or have all the services calling the same database, you can use events so these systems copy the same information from the same source. Also, when you want to have parallel processing, if you have multiple services that you need to execute at the same time, event-driven architecture works really well with this. When decoupling is very important and you have maybe different heterogeneous systems and you want to have all of them really decoupled, then event-driven architecture is really good for that because, as I mentioned before, the contract becomes the event. And as long as you respect the event, then all the system will work. Now let's see this with an example. Let's go back to our e-commerce site system that we worked with in the software architecture introduction series. Let's say our user has gone through the website, browsed some products, added to cart, and now is ready to buy. After the user clicks on the buy button, maybe our system can trigger an event called product purchased. And this product purchased event can have some data. And this product purchased event can be processed by different systems. For example, it can be processed by the inventory system, where it will decrease the inventory for that product. And it can also be consumed by another service, for example, the recommendation service, that will be processing this for future recommendations for our user. And this is where we are going to get into the beginning of the video. Because in this case, you can see that indentation matters. In this case, we just sent an event and different systems can consume it. And we are not expecting from the store or from the UI, expecting a response from these services. We are just sending the event and any system interested in this event can subscribe to it and execute the task that they need. But on the other hand, let's see another example where this is not the case and we are actually expecting a response. In this case, the user clicks the buy button and we want to confirm the payment before we ship the products. So we can still do it in an event-driven system. We can send an event, for example, called confirm payment with additional data. Then the payment service will read this event and process it and see if it's successful or not and send a response. As you can see in this case, it's very different from the first one, right? Because in the first example, we didn't expect a response. In this case, we're expecting it before we do other things. There is also some minor differences that notice the intention of the event. In the first one, we just said something that happened. We said product purchased. In this case, we're saying confirm payment, right? The verb has some intention about what we want to do. And even though it's decoupled, like the UI service or the store service doesn't need to know about the payment service, it is expecting that another service will do something and send me an event back. So it is, in that case, it's decoupled, but the response is still required. And we will see why this is important in the next video in the series. And that's the end of this video. If there is something that wasn't clear, just ping me in the comment section below and I will try to reply to them. Also, don't miss the links that I put in the description where I point to the presentations like I mentioned before, the Martin Fowler's presentation.
the discussions is about the event driven architecture, which is also in consonance or in connection with the software architecture. Okay, so I think that's it for my sharing, no, regarding the software architecture.